Good afternoon, everyone. This is lecture 23 of PTRE 475-575, well completions and advanced stimulation techniques. And this will be the last lecture before the exam. So we have an exam next Thursday. The exam will be, as I said in the announcement, from module 2, slide 21, all the way to the end of module 3. I promised to let you know by the end of the week, but it became Saturday until I was able to finish the exam. And I decided let's not put module 4 stuff yet in the exam. The exam is fairly simple. Remember, this is a 50-minute exam, but I'm giving you 75 minutes, so don't worry about the time. Worry about the quality. Okay? Worry about the quality of what you put in the, or you write down. Now those who didn't, I mean, you already have the experience of the first exam, so it shouldn't be that bad. It shouldn't be that bad. For the review, we can do it many ways. If there is existing questions that you want me to get over, I can answer them. Or I can go over the slides, and then if you have any questions, you can stop me. Or if you have any more questions at the end, we can do it any way you guys like. So I guess if there is any questions, please let me know. Otherwise, can put it in. Meanwhile, 1 second, I want to make sure exam. I want to be able to be seeing the exam. Hello? I want to be able to see the exam when I am midterm. For exam 2. Okay, so it's here. So it's the same blend that you are used to, like mix and match pairings, some true or false, some filling the blank. I think you are very used to this stuff. And then there are some questions similar to what you have seen in the homework. By the way, homework 3 grades are up. If you cannot see them, it means accidentally I didn't make them post us, but I think they are already on Blackboard. They should be already on Blackboard. And they were not terrible. They were pretty good, actually. It was something like, where is it? 98, 95, 91, 87, 86, 85, 84, and 61. So pretty good, pretty good. You guys, yeah, so we can basically, where is it again? There is some mathematical questions, some conceptual, but really there is nothing that will take your time. Some of you will be able to finish in like 25 minutes or maybe 30 minutes, and then it would be wise if you sit down and check the math. And then leave it. Don't leave early. But I don't think time will be an issue in this exam. Let's put it this way. Anyway, let's start. So we talked a little bit about packers, and this is not a brand new topic. You have seen it in production already. So I wouldn't worry too much about packets for this exam, other than knowing the basics. It's a device that is run into the wellbore. You achieve separation between the tubing that is inside the packer and the casing that is outside of the packer. You create hydraulic separation. There is two types, permanent and retrievable. Permanent, obviously, is stronger. They cannot be unseated that easily. And there is several deformations that the packet can go through. Like piston deformation becomes shorter, buckling, ballooning, temperature. Some of you will be working with geothermal, not as many of you as, it's not going to be, many of you would like to work with geothermal, but I think geothermal, it would be a function that might go away by some time later. So, but some of you regardless will work with high temperature environments. And some of those tubing movements would be important. It's basically a summation of the forces in the y direction. And we showed how you do it mathematically. Don't worry too much about this stuff. So any kind of procedure that you do can influence the packer, and at extreme situation, it can get unseated. When you run the packer, you can damage existing packers or that itself. Putting the well on production is like starting the flow. You can unseat the packer, swabbing, taking a sample, acidizing, obviously, fracking, any kind of operation you put the well in, you can influence the forces acting on the packer. After the packer is set, each subsequent operation must be evaluated against the original setting installed conditions. Exceeding the original setting forces might cause retrievable packer to move, sealing sub to slide, and a sealing sub to slide out of a permanent packer. That would be damaging. Okay, let's move on a little bit. Pressure changes. We talk about forces acting on a packer body. These equations, see them, but I wouldn't worry too much about those. Okay, I wouldn't worry that much about this, especially those equations with the weird conversion factors. If you need it, I will give it to you. So don't worry too much about that, because this is production. We saw some problems. And then remember, the solution that we put is that you have a force acting on the packer, pushing it upwards. And we said, if we apply a force down to balance it, we can backward. So it's not a good idea. A good idea is to increase the pressure in the annulus, pushing the packer down. So instead of pushing the tubing down. So that way you balance the forces. Robert. Excuse me. Pumping down in a wireline operation is basically all about how much fluid you need in the surface, and then how much down after that, how much downhole you have been able to reach. And we saw some example actually at the end of homework 2 that were not in the exam, I think, but ultimately you have the slip page on the surface, some surface equipment taking some volumes, and then you have the volume that goes down hole, and then you have some safety factor, etc., etc. Nothing crazy. I think in the homework we didn't even have anything on the. We said assume 0 on the surface, so no big deal. said the lubricate or length is important, practically speaking, so that you can remove the fish that you are taking out. And there are some operational stuff about wireline operations here. Make sure you look at them. Again, I wouldn't be dying for it too much. Don't break your back for those stuff. And now, pub joints are markers, and they are smaller than normal joints. So you put them after every few depth increments, and you know how far you are. Perforating operations. Before that, perforations are important. Bullet perforating is the original type technology. It is a problem because it leaves behind it a lot of waste, and that waste stands in the way of production. This bullet at the end, it stays there at the tip of the crack of the perforation. So basically, the tip of the perforation becomes like solid metal. It's like it has cramped solid metal there. You cannot use that for flow. So it's a it's bad it's a bad it's a pitfall of an old method of perforating a web. Now, jet perforating is more modern. It's using energy to create this. You don't have the bullet left, but you have a lot of debris, and the debris can be removed by acidization, by acid wash. Now you cannot melt the bullet that easily, or if you are gonna melt the bullet, you are gonna melt other stuff on the way that you don't want to. So there are some things you can do about the bullet, but not very effective, to be honest. Jet perforating is obviously superior. It's a more recent invention, and you have the shape charges, etc., etc. We did talk a lot about the details, but I don't want you to worry too much about those. Just read them a couple of times, make sure you know how it works. That's about it. I mean, things that you can play with is perforation diameter, perforation length, phasing, and shot density. And these are tools that you have controlled by the practitioner on the surface that you can exploit later on when you do the actual stimulation. Okay, it can be you can play with limited entry, or you can achieve limited entry by playing with perforation diameter, perforation length, phasing, etc., etc. There is several people who said that in order to get fractures oriented the right way, you have to have perforations in one angle only, like up and down, 0 and 180, or left to right, 90 to 70. That is called oriented perforating techniques. It's harder to get perforations that are at a 60-degree angle than at one angle. So if a single phase perforations or oriented perforating techniques are ideal, it's easy to achieve. Shot density, it has a limit as well. You cannot have a lot of shots per foot, then you are weakening the casing too much. You are dealing with other issues. But generally, all this stuff, to a large extent, are controlled by humans, and you want to manipulate them for your own benefit. I mean, some people say perforation diameter plays a bigger role. Some other people say perforation length. Perforation guns, I mean, all kinds of these are man-made tools. I mean, they get developed by the service companies and they become better and better by constant feedback. They are being used constantly. They come with experts, and they are run down whole and then basically operated to create those perforations. The design plays a role. It can be manipulated. And then, yeah, maybe it's smart to have somebody. If you are going to change the design the last minute, you may need to have an expert on the field with you. Now, remember this little lip on the perforation by the casing flowing out? It's called burr, B-U-R-R. And then the perforation becomes thicker because the young modulus of the stiffness of the cement is smaller than the stiffness of the steel, obviously. And the stiffness of the rock is about the same as the cement, more or less. So as the perforation moves in the perforation tunnel, as we move far away from the well, the perforation, the charge loses energy. So, or the energy jet, let's say, loses energy, goes less and less, so it slows down and then it stops. But generally, you have a clean perforation tunnel, which is not the case with the bullet perforating techniques. It was not the case with bullet perforating techniques. And obviously, you have an objective. You don't want to damage the well integrity. You don't want to have. I mean, this burr, B-U-R-R, like a leap, helps a lot with preventing microannulus, but many times you may get the microannulus created because the layers, that casing, cement shed, rock formation, it has two interfaces that we need to worry about. And all the layers can suffer damages, so be very careful. It's things that you're going to be worried about if you're an operator when your well is undergoing perforation. Debris, I mean, you're going to do the acid wash. It can really be bad for your production at severe cases. We spot acid pre-flush. Well, acid pre-flush is before we do fracturing, but acid wash in general is to clean up the perforations. And you need to be very, you can use very strong acid and you can use very weak acid. The weak acid is not going to clean them up well. Strong acid may damage them too much. So you need to be very, very careful in this design. You need to discuss with the company, that the vendor that provides you these solutions, see what people in the nearby wells are doing, and so on and so forth. Okay. And we talked about that, is what I mentioned earlier. This equation is basically the volume of a pre-flush is equal to the volume of pump down to make it to the depth that you want, plus the safety factor, minus the flush. All volumes must be in consistent units. I think this equation was confusing to students. So we make some examples. One example, here, one example here. But I think the homework was much easier. I think we got like no slippage on the surface. We simplified the problem. Okay, so the volumes are important. Now, sand control, how do you keep sand out of the well? You need to use some kind of a liner or a sand pack or a gravel pack. Well, liners can be combined with gravel pack and those stuff. We talk about some equipment. We have the liner here with small slots. We have pre-drill liners. We have wire wrap screens, gravel pack screens, premium screens, expandable screens. Now, some of you, I think, are taking design classes now, and you are designing your wellbore architecture. These are stuff that maybe you consider in your project. I remember in my time when I was taking senior design, that was spring of 2013, so 12 years ago. It helped our economics a lot by not doing perforations and using a pre-drilled liner because it was a sandstone reservoir in the East Texas, and permeability was good. We really didn't need perforations. We just like use a use a slotted liner or a pre-drilled liner. I don't remember what we use specifically, but you get the idea. Now, for sand, you can go more exotic, like what is in C, gravel pack screen. Okay, more exotic means more complicated, but it can help eliminate some kind of stuff. So they are not useless. Let's put it this way. Okay, wire wrap screens. I think you know how those work. You have the rib holding the base pipe and the screen wrap wire together. And basically, you want to keep the sand from coming into the well. It's like you are filtering the sand out of the well. And it would be that's one way of doing it. And then you have gravel pack as well in between. You can have, you don't want the gravel pack to get cluttered. So the gravel pack is a little bit of a, how do you call it? Like, it's a little bit of a compromise. It suppresses the flow into your well. You want it to act as a filter. You want to keep the bad things out of your well, but you want to get the stuff that you want into your well. So it's a little bit of a compromise. You know, it's like you are restricting flow into your well with a gravel pack. So if you use a gravel pack that restricts the flow too much, then oh my God, you are not going to get any flow into your well. But it can be very useful in keeping fines and loose sand particles out of the well, especially if you have your well on a high production. Other types of screens are described here. And then this is an important slide with the 3 common multi-stage stimulation techniques. Plug and perf, pretty traditional. All activated completions, more exotic, more like early 2010s. And then coil tubing activated completions, more like mid 2010s, a little bit later, just before COVID. Yeah. Then plug and abandonment, that's an important part. At the end of the life of the well, there is a lot of discussion today because plug and abandonment jobs by big super majors not done properly in the Permian, and then you inject nearby, you do anything nearby that increases the pressure, and suddenly you get what they call zombie wells, which I believe is a trademarked term, zombie wells, like wells coming to life, start spewing brine at burst. Some of them are spewing methane. Methane is very, very dangerous. Methane is dangerous because it's very flammable. It really wants to become CO2. So if you go with light a cigarette near a well that is leaking methane very slowly, oh my God, you'll become an astronaut involuntarily. And same way, though, if you have a well, hypothetically speaking, now, because I know there is a lot of operations related to CO2, if you get a blowout with CO2, it's a very hard blowout to deal with because you cannot really flare it. If it was a blowout with methane, you can flare it, and that's it. But a blowout with CO2, oh, yeah, not a good idea. So pros and cons with everything. In fact, I don't believe that if the CO2 storage narratives continue, which I think they have slowed down recently, the fashions have subsided on that because other fashions came in, geothermal, this kind of stuff. If that's the case, and we end up having a bunch of wells that are injecting CO2 as a bulk injection, not as a CO2 EOR, which is basically you inject CO2, you produce oil. The wells that are specifically for storage of CO2 using bulk injection, those wells should be able to hold pressure. And they need a lot of pressure to inject. And there's a lot of damage on those. I wrote a paper last summer. I published a paper on that. So many damages they can get by the increase of pressure that you may find how do you call it, bad for your casing, cement, rock formation system. But we will end up having a lot of blowouts with CO2 that are going to be hard to deal with. And at the same time, we are going to have a lot of well integrity issues that we are going to have to come up with, in a sense that we'll have to develop cement recipes, expandable cements, pressure resistant cements, cement recipes, etc., etc. 2 years ago, 1 year ago, no, I think it was last year spring break, or last year spring break. I was at Colorado School of Mines, and I went to see my old office, and I was a postdoc in civil engineering, actually, there in the year of 2022. I was doing research on tunnel stability, which is very similar to oil and gas, but perforation and wellbore intersecting. But anyway, I went to see some people, and there was a postdoc there working on a new recipe of cement for construction reasons that is, I think, fully magnesium oxide or something. So when you try to cure it, it becomes key. So a lot of interesting things going on. A lot of interesting things going on. Now, plug and abandon techniques. There are several techniques. Now, we understand the necessity that we need to do properly plug and abandoning of a well, because we really don't know what kind of pressure the well would be facing after it's plug and abandoned, maybe 10 years after, if you increase the pressure in those wells. But you can do something like a bridge plug, which is a man-made plug, along with some cement slurries, to ensure that it's like a champagne bottle and you have a cork. You need to make sure the cork can hold the pressure inside. Generally, the pressure inside the champagne bottle is 6 to 7 atmospheres. And the pressure on the other side of the champagne bottle is something like 1, right? It's open air. So you want to be able to hold that differential of 5, 6 atmospheres. Similarly here, you need to make a plug and abandonment design that should be able to hold pressure as much as possible. And then there is several ways of degradation that you need to consider. You have cement inside the well, it touches casing, it is steel, then it touches the cement on the other side, and then it touches the rock. You have 1, 2, 3, 1, 2, 3. Yeah, 3 interfaces you need to worry about. Cement, steel, steel, cement, cement, rock. And then you need to worry about the cement itself inside the well and outside of the well. So 5, 3 plus 2, 5. And then you need to worry about the casing leaking because it got degraded. 6. And then you want to worry about what is it? The cement itself leaking. 7. And you want to worry about what angles, interface. Yeah, also across the annulus cement connector, also basically across the cement shed. The cement shed in general is a weak point because it's okay, you run the casing in steel as a whole, but then you run cement slurry, and the cement slurry may not be going fully through the annulus. So they are it's human related, it's human limited operation. So it might not be excellent. Remember, the whole Macondo disaster happened because the cement job wasn't good. It started from there. But yeah, you need to worry about all these possible failures for well integrity. Okay, now any questions on module 2? Okay, let's do module 3, which is the longer one. Stop me if you have any questions. Fracking, why, how, and for what? We stimulate wells using fracking. We increase the permeability inside those fractures and help fluid flow into the well. We increase hydrocarbon production, which is the main goal, basically. Historical background, we talked about those people, very important people. Well, one for the good and one for the bad. Frac spread, similar to a drilling rig. You have similar setups. Every company does the frac job differently. They will have some deviations in the way they do their job, but ultimately it's similar. The layout is similar. It hasn't changed that much from the beginning. Modern day operations, now you have simultaneous operations. You are trying to stimulate multiple, how do you call it, multiple laterals at the same time. It's a little bit more complex, but not very different. You pump water along with some sand down hole. You open fractures. You fill the fractures with high permeability sand, and then that's it. As you go deeper, the fluid goes deeper. It gains pressure. In the surface, you also apply pressure, and then you fracture. Fractures open, crack the rock, and then assist fluid flow. Every equipment that goes through pressure, it has a low pressure side and a high pressure side. Be very careful with this stuff if you are in the field, please. And then you make it to what we call the frac tree, which is on top of the wellhead. And what you have there is the surface treating pressure. And you need to make sure you don't exceed a certain value, because then you are going to be in trouble. This is, you have on the right, if you see my screen, my mouse is the missile, and then the monoline. Fluid flows like this, or like, I think this second picture is more clear. The well is that way. And then you see the behinds of the frac tracks that help increase the pressure in the missile. The monoline. You can achieve the same result with a more complicated equipment, all connected together. It is not a very good. It's not a very good idea, because you have a lot of. If you have a lot of connections, every connection can leak. Well, in fact, all connections leak. It's just you want to make sure that they don't leak at a high enough. They leak sufficiently slow. Let's put it this way. So if you have one piece of equipment, you have like only you reduce the amount of failures you may encounter, but any failure is more costly, and more like impactful adversely to the whole operation. If you have a big equipment that is hard to replace, being decommissioned for a while because of repairs, then you are in trouble. This is how a frac tree looks like. It's very similar to the BOP. It's basically, the BOP is there on the wellhead when you are drilling, okay? The cementing head is on top of the BOP when you are cementing. The Christmas tree is on top of the wellhead when you are producing. The frac tree is on top of the wellhead when you are doing a frac job. It's gonna be the company who comes over to do the frac job. And yeah, I mean, it's basically very similar. It has valves and switches and line going in, line coming out. You can inject, you can produce, flow back. Produce means flow back.
I have a question, Professor.
Sir, yeah.
Can we put a wire line in this tree or not?
Well, you want to run a wire line to do like a coil tubing?
A wire line, for example, maybe to do logging, for example, while fracturing?
No,
No?
not with this wellhead.
Okay.
Not
So-
with this wellhead.
So
Because
mainly this is only for controlling pressures and pumps. Okay.
yeah, this is high pressure. Now, you can inject fluids, you can flow back, but this is gonna be put there to run the fluid that you want downhole, run the solids that you want downhole for the frac treatment, then do the flow back. It's generally gonna be a separate company that will come in and do the flow back. And then you're gonna leave it, take it away, the frac tree, and put a Christmas tree when you are basically producing the well. It's gonna be like that. This is for a special operation. And I will say that this frac tree has less functionality, but higher pressure rating than the what is it? Than the
Christmas tree.
Christmas tree, yeah, and about the same, if not, yeah, about the same pressure rating with BOP, or is it? The BOP generally can hold higher pressures because when you have the blowout, all these things can play. It can lead to very high pressures during drilling, but generally, frag operation is when the well will feel the highest pressure. So you need to be able to hold that. It's a specialized wellhead. Now talking about pressures, you need to be able to relieve the pressure if it goes off hand. That's why you have the pop-off relief valves. They just start bleeding fluid if they go if the pressure exceeds a certain value. Generally, leakage of fluid, the spillage of fluid, the fluid is not is not hazardous. It's basically water and sand and some chemicals like glycerin. Most of them are mild chemicals. It could be something more hazardous like acid. It's not a terrible, environmental, ecological wise catastrophe, but you will have to report it. What many companies do, I know that Liberty is doing it, when they start their frag operation, they basically put something like a nylon at the bottom of their layout. So it's like any spillage on their part can be basically controlled fairly easily. It's a very controlled environment. It's like quite clean. Actually, if you go to a drilling rig and a frac site, the main noticeable changes that you are going to see is in the cleanliness. It's a cleaner operation, hydraulic fracturing. Similar to drilling, we have something, we had something called MASTP, maximum allowable surface treating pressure. Generally, if you're injecting from tubing, you want to have the surface casing at like almost zero pressure. But as you inject, the tubing expands, it pushes against the casing. So you may get a small reading of pressure on the casing, but shouldn't be that terrible. You need casing to protect the aquifers nearby. Yeah, I mean, that's what it says here. The monoline, you want to reduce the amount of lines. Remember, many lines, many connections, every connection can leak. Manifolds are Yeah, reduce the number of joints. Joints can leak. Isolation valves. Sometimes you have a leakage and you really don't know where it's coming. We call it wash. You need to find where the leakage is. You read the leakage as dropping pressure, but you really don't know. It's like you have a tire, you have a flat tire, you lost the pressure of your tire, but you really don't know where is that leakage coming from. It could be, so you pump air on the tire, you put some soap around it, and hopefully you are gonna see bubbles. If you don't see bubbles, it might be the leakage coming from elsewhere. It might be very small, so you can see it as bubbles. It might be in a weird side, or it might be that you hit the rim of the car very hard on the pavement. You bend it, and now you are leaking. The tires are leaking. That would be a harder fix, but you may have other indications of this kind of failures. In the rigs, drilling rigs I used to work on, we had some people who were being nasty to each other, and they didn't want to slash the tires of each other because it would be highly unethical, one thing, and then it would be like, we were driving like 6 mile this road in the middle of nowhere. You really don't want to do that to somebody. And then you have to drive 1 hour to the nearby city. So they were just removing air from tires. And just basically just remove the air of the tire. If you get caught, at most, they are gonna make you feel the air, the tire that you deflated. And all of us had like electric compressors in our car. I still have mine. I had a friend that he got a flat tire. We tried with soap, we couldn't find the leak. And then I told him I will drive behind you on this road. And then, so if you get stuck or something, I will help. But then we have to drive to the city and take the car to the shop because you really have an issue. And we put a lot of air so that he makes it because we knew he would be, for 1 hour, he would be losing pressure. It was past Barstow, Texas. We are going to Pego City. And at the end of the lease road, he told me, I think it's good. I think it's fine. We don't need to take it to the shop. And I was like, are you serious? How did you lose air in the first place? It was material balance. But then we took it to the shop, and indeed there was a puncture, a slow puncture. Anyway, similar to the leaks in the field, if there is a leak, a wash or something, just like during drilling, you need to find it. And it's not very easy to find it. You can waste a lot of what we call NPT, non-productive time, in doing it. Non-productive time was a term used in drilling when you are actually not drilling ahead. You are doing something else that it is for the entire, it is needed for the operation, but you are not actually deepening the hole. Nowadays, because there is a lot of fracturing is very much similar to a manufacturing process. We fracture, we zipper frac, we do a lot of stuff. Do multiple laterals at the same time, and so on and so forth. There is a non-productive time concept used in fracturing operations as well. You want to limit the time as you go from one lateral to the next, if you are stimulating them simultaneously, and so on and so forth. This is an important plot. Make sure you know it. Leak of pressure, FPB, FPP, then fracture propagation pressure, not to be confused with formation pore pressure that we use during mine drilling classes. instantaneous shedding pressure. We assume that is about the same as SH mean, fracture closure pressure, and then we said that fracture initiation pressure is between leak of pressure and formation breakdown pressure. Now, if we do diagnostic fracture injection test or diagnostic formation integrity test, I saw them written as both. Basically, what we do is that we do multiple cycles. We open a fracture, so we crack the rock, and then we remove the fluid, and then we pump fluid again. So we open a fracture, we crack the rock, we close it, and then we go and open that particular fracture. So the second time we try to open that fracture, you don't have to beat the tensile strength of the rock. So the difference between the crest of the first cycle and the rest is roughly equal to the tensile strength of the rock. Is the apparent tensile strength of the rock, as we call it. Fairly smart way to do it. Now, fracture initiation, we need to look at the stresses on the wellbore radius. This is for a horizontal well along SH mean, assuming that SH mean is parallel to the y-axis. And we said that if you want a expression for the initiation of a longitudinal fracture, you want this to be more than minus t. So what you do is you come here, set this minus t, and solve for PW as if FIP is identical to PW. Now, and then you get an expression for the PW for a longitudinal fracture initiation. Now, you can do the same thing as for the transverse fracture initiation, but the problem is that there is no PW. Now, this is one model, though. Very, very simple model, linearly elastic with static pole pressure. There is more complicated models that may have sigma XX or sigma YY, the axial stress, having a component with PW. So you may have a PW here or something, a component with PW. And then you can be able to solve for an equation of FIP, fracture initiation pressure, for transverse fracture initiation, using basically set it equal to minus t and then solve for PW. This is what basically we're talking about here. If we assume that the wellbore is not there, FIP for is very easy. This, just like your just like your homework 2. If you assume it's longitudinal, you can do it. If you assume it's transverse, you need to do it. You need to find an equation that has a PW term, which they are available. It's just they are more complex than what we see in class. You may see one, who knows? So, fracture geometry, you had a homework question, homework 3. I gave you the equations, and I think you learned how to use it, which is important. It looks ugly, it looks weird. Make sure you use it in consistent units, and it's easier to do that with SI, to be honest. I'm not a particular SI units fan. I was, I guess, when I was young, it was we were converting from SI, no, to SI from like English units or British units. But now when I came to the US, I learned how to use oil field units, like which is related to British units. So I think just like you guys are more comfortable with oil field units. However, for these equations, these ugly terms, 4/9, if you do a dimensional analysis of that, you need to remember the indices. So TI minutes to seconds, you need to have like seconds divided by 60 and then raised to the power of 4/9. What is 1/60 to the power of 4/9? It becomes a little bit messy, you know? So, yeah, we have the models. The easiest model is the coin shape model. You don't have height, you don't have length, you just have width. Which is you just have, sorry, you just have a radius, which is equal to height and length, and then the width. Pseudo 3D planar fracture geometry, you have the KGD model for a very tall fracture. Fracture is like that. The well is like this. Fracture is like that. Width stays the same along the height, but changes along the length. The equation is given by this. The maximum width at the wellbore, or W max, would be given by this equation. Now, bear in mind, what I was going to say is that I forgot something about the. Oh, yeah, important thing. No, I didn't mention during the lectures, I think. We said height, length, for a vertical wellbore. For a horizontal wellbore, it's like this. So this is height, and this is length. Length is how far you go away from the well. So remember that to draw what I'm trying to say here is that if this is the wellbore and this is the fracture, this is actually the height of the fracture. And this is the length of the fracture. That's what I wanted to say. Some of you may be doing projects for grad school related to fractal geometries and stuff, and I want you to make sure that you have that. L is sometimes denoted by XF. PKN is very popular. Oh, this is still, sorry, this is still KGD, I think. Yeah. This is how you get the length, and then you have the P net pressure of a fracture, which is a very important term. Is the pressure of the fracture against the stress you are operating against. For a horizontal well drilled parallel to SH mean, if the fracture is transverse, this would be SH mean, S3 would be SH mean, and a lot of debates going on about understanding a defeat graph. It's a lot related to the fact that sometimes if you do a diagnostic fracture formation integrity test or fracture injection test, whatever, or fluid injection test, I guess, you might misinterpret it and read a very small value for S3. If you do that and you read a very small value for S3, you are going to get a very huge value for the fracture pressure, the pressure of the fluid inside the fracture. It might be very unrealistic. This is an equation for the net pressure, which, yeah, is equal to, oh, sparked. P frac minus S3. Let's move this here. Beyond the better far away than sorry. Anyway, I think I was doing this on my shirt and it drew charge on my hand. And then when I went to touch it, it was metal and it had charge on the other side. So it made current flow. But anyway, yeah, this is how you calculate the P net for the KGD model. KGD is used for, it's very good for like frag and pack operations, etc., etc. Now, PKN is more similar to, is more for stuff that you guys are interested about, horizontal well transverse fractures. Many models, they start the fracture as coin shape and then it becomes PKN. This is the equation for the width, which changes with obviously with time, but also with the length as you go in. This is the length or half length, and then the P net, and the volume of the fracture is given by this equation. If you have to use these equations, you will be given. You don't have to memorize them, but I want you to be able to use them. So that's why I gave you the homework. Is giving you the homework, you learn how to use them. And now you become like, it becomes like an easy thing. You may want to know how to use those fractions, these equations, sorry. This is a comparison between the three models. I want you to be familiar with those. Fluid leak-off, you really need to take account of fluid leak-off. There is the Carter model for fluid leak-off from 1952, which is very similar to the mud cake formation in drilling. It's basically, it's quite similar, as I think Shamel said back in that lecture, similar to Darcy's law, kind of, with some differences. Fracture geometry will impact the flow through the well. I don't need to tell you that, you already know that. Carter fluid leak-off model is fairly simple. And then fluid flow through an open fracture. Remember the lubrication theory? It basically, if you double the width, the flow through the fracture is 2 to the power of 3. If you make the width times 10, the fluid flow through the fracture is times 1,000. It's 3 raised to the power, it exponentially increases by an index of 3 Q frac. So remember that now, multi-frac complexities, we get more into the real world. You have simultaneously growing fractures interfering with one another. This is not helpful. And you have something called stress shadowing. The stress shadow is always in the direction, is compression, stress compression in the direction of the width of the fracture. So if the fracture is opening against SH mean, the stress shadows increase SH mean. As a result, increase SH mean, it reduces the difference between SH max and SH. As a result, we become It makes the fractures to turn, to swarm, etc., etc. It leads to non-planar fracture growth, hydraulic fracture swarms, hydraulic fractures ending prematurely, reducing the resistance, the resultant, stimulated reservoir volume, and obviously it leads to suboptimal economics at the end of the day. You see here from a simulation, stress shadows makes the fractures grow very dissimilarly. You have, they say, more losers than winners. And there is something you can do about it. It's called limited entry. After Lagron and Rasmussen's work from 1969 on vertical wells, now you have the adaptations of that for horizontal wells. It's stuff that we mentioned earlier in this lecture, variable perforation number and diameter, perforation cluster spacing, something that I did for my master's, and so on. I gave you a magazine article to read about it. And then there are other complexities in multi-frag growth from horizontal wells. These are complexities you cannot easily include in a model if you have a computational simulator, but eventually a good simulation model will have to be able to include that. In general, I think probabilistics is the best thing to utilize for this stuff. Probability, I guess. A probabilistic predictive model would be much superior. Non-simultaneous hydraulic fracture initiation at the same stage, fractures not initiating at the same time from the same stage, dominant or runaway hydraulic fracture creation, inactive perforation clusters, and hydraulic fracture reorientation in the near wellbore region. Flow regimes through fractures, we have linear inside the fracture, linear from the fracture into the rock formation, bilinear inside the fracture and the rock formation, and pseudo-radial. Then, by putting many wells near each other, we have what we call frag hits. That wasn't at all a concept when I was a student, but because we frag wells near each other, we get wells producing fluid that was used to fracture the neighbor well. It's bad even if it's your well or somebody else's well. These are new kinds of problems. How do you suppress it? You need to play with the spacing, stage spacing, stage separation, and even sequencing to fix that. We talk about the Texas two-step, that is a technique for limited entry, ultimately, or for stress shadow mitigation. But yeah, ultimately, you want to maximize the net present value from your wells. And where is it? I mean, we don't want the thing you know about this. Economics, basically, for a hydraulic fracture treatment, the net present value equation becomes simplified to this. You don't need to discount the cost because they happen immediately at the beginning, but you need to discount the revenues because you keep the well producing for hopefully years after the stimulation. So we care about the frag geometry. We care about the stimulated reservoir volume. From frag geometry, we get the stimulated reservoir volume. Then we have the effective prop volume. We have something called IPR curves, inflow performance relationship, which models how the reservoir behaves. we assess well deliverability. We're going to see that in module 4. We do decline curve analysis, how the production will decline with time. We feed those curves. And then we use a pricing index to calculate the annual revenues. Apply the total cost, and then we optimize for the economics. We want as much net present value as possible. Net present value is how many today US dollars is this project. Like everything. The cost of the project, the benefit, the revenues of the project, all discounted with time. And I have a nice article on the way ahead you can read about this topic, which I wrote when I was a PhD student. We saw how we expect the money to vary, and I think you had a homework question about that, and a simplified case. We start by putting money on the project. That's the money that we pay for the hydraulic fracture treatment, something like $100,000 or $200,000. And then we keep producing. Our well is producing more and more and more and more. The more the well is producing at a reduced rate, at a decreasing rate, but the more money we make, the higher the curve goes. And hopefully it's going to go higher than zero. Whenever it touches zero, that's the payout period. And then the discount rate at which the NPV becomes zero at a certain time point is called the internal revenue, internal returns revenue, IRR, internal return. I forgot what is the name. Let me see, so I don't say anything wrong. IRR, economics. Internal rate of return. Sorry. Yeah. Then we talked about fracture propagation. We have a crack, we are extending it. We made some assumptions. We talk about Griffith's theory. Griffith's theory doesn't work very well. It gives you infinite energy at the crack tip, but we make some adjustments to make it work. And then we introduce the concept of fracture toughness. You need the stress intensity factor to overcome the critical stress intensity factor, also known as the fracture toughness, in order for the fracture to keep growing. And fracture toughness is given by this equation, weird units like MPa square root meters or PSI square root inches. But it's very easy to measure it using an SCB test. It's a weird shaped sample. It's a semicircle with a notch at the middle. And then you make these measurements, get the data, and apply this equation. There is better versions of this equation for research, but for classroom, I think this is good. You measure the rate at which, the force at which it cracks, and then WPF max, pi is pi, you see, alpha is the notch length, which is a constant, T is the thickness, R is the radius. You want your S over R to be roughly 0.8. R is the radius of the sample. And you want A over R to be between 0.1 and 0.2. Then YI would be for 0.5. Again, this is rough estimates. This is rough approximations, but yeah. I'll show you some SCB tests that I ran when I was young. I wish I could go back in time and do them better. But ultimately, You measure the how brittle the material is, basically. The higher the fracture toughness, the less brittle it is, the more ductile it is. And actually, geomechanically speaking, ductile and brittleness, they are not antonyms necessarily, but for the class purposes, I think it should be okay. The best person to explain that to you is Dr. Schultz, actually. I remember him talking about that since like 2015, 2016. Some example problems. Unconfined compressive strength. What does it give us? It gives us the UCS, but also the slope here will give us the slope of this will give us the Young modulus, the stiffness of the sample. Now, if you use some confinement, it becomes confined strength, and then basically the strength needed to break the core in shear becomes much bigger than UCS. UCS is where the mouse is. Now, UCS is this. You apply a little bit of confinement, and then you need to get here to break it. That's the more Coulomb diagram. If we assume an intact sample, like when we do core testing, come on. Cores intact, you need to consider a CO. If it's a pre-fracture sample, like a big rock mass, you can assume that this is 0. How do we measure the tensile strength? With something called the Brazilian test. It's actually easier than a UCS test. Again, you put it into the loading frame, you break it, and you measure the force at which it breaks, you divide by pi LR, and then you are good. These are easy. Step rate test. Now we move from lab scale testing to field scale testing. You have to do it if you are going to have an injection well, the law tells you you need to do it in Texas. Oops, sorry. You basically want to see if the well is able to hold those injection pressures. But as you inject, you will notice a change in the steps. You are going to start losing pressure at some point. The pressure goes up, but not as high. So the steps get distorted. If you plot it as a point of pressure versus rate, you are going to get two lines that meet. Where they meet is the FPP, or the formation partitioning pressure, which is like, it sounds like a rupture pressure. It's very similar to fracture initiation pressure, but it's not quite the same. No? It's not quite the same. Formation partitioning pressure. Many times I told you the stories about the wells in Alaska that they were injecting cold water in and they were fracturing them unintentionally. Same thing here. You need to make sure that the well is going to be able to hold the pressure that you intended to subject it to. FCP. Now, if you make a plot of the pressure versus the square root of the time after shut-in, you're going to have a noticeable change in the slope. At that point, we call that pressure where the slope changes, the formation closure pressure or the fracture closure pressure. It's roughly equal to S3. So for normal and strike slip faulting, SH mean, for reverse, SV. how fast the fracture propagates. We talk about the paper. And then we have finally other well stimulation techniques. An important one, matrix acetizing, explosive fracturing, and very importantly, gas lift, which is many people are telling me, why do you do artificial lift in a well completions with advanced stimulation techniques class? And I tell them, one is that they should know it, they have seen it in production, and two, gas lift is considered a stimulation. So, yeah. And the other reason is that we don't have an artificial lift elective course in this department. And I know that in other departments, they do have them. So they are important. It is an important topic. I know you covered it a little bit during production. Anyway, so good luck in the exam. I'm gonna be available tomorrow, office hours. If you have any questions, email me. The TA is in town. He's available too. Any one of us that can help you, any question, answer any questions that you may have. And I will see you. I won't see any of you on Thursday, but yeah, the exam is gonna be at 12:30, and you have 24 hours to start the exam. And once you start the exam, it's gonna be 75 minutes. Thank you very much. Have a nice rest of your day. Thank you, Donald. Thank you, Shamel.
Thank you, Professor. Have a good day.
Yeah.
Great. Thank you.